So today we're finishing up vectors. We're going to talk strictly about vectors in the coordinate plane, and you want to have a unit circle for reference today. On worksheet 3, that's where we're going to see all the formulas we're going to be working with today. So vectors in the coordinate plane, there's going to be some vocabulary and some basic operations that you need to consider, but it's really not too bad. We have our vector, which is in component form. Remember, it has a horizontal and a vertical component to it. We're supposed to be drawing the vectors to scale. I keep skipping over that part because I can't draw to begin with, but every time we do an application question, I'm supposed to set up a scale, like 1 inch equals this many meters per second, and I'm supposed to actually measure that out, but you know me, I'm not going to do that. So at the very least, and I don't do a good job of this either, when you guys do your vector applications, you should at least make them like relatively comparable. So like for instance, the airplane question versus the wind question. If the airplane is going 500 miles per hour and the wind is 30 miles per hour, you should make sure that the wind vector is significantly smaller than the airplane's vector. Okay? Otherwise your triangle will look really strange. And again, I do a terrible job of that, but you guys might want to think about, as you work on your homework, improving your pictures a little bit. Definitely improve them over mine. Mine are terrible. Alright, so we're going to be looking at equivalent vectors throughout the coordinate plane. And let's talk about operations. So this first operation, this is from your textbook, not on your notes yet, but they're going to want you, okay, there we go. They're going to want you to investigate the component form of a vector, which we kind of already done this, but this time they're going to give you a formula. And notice it says x2 minus x1 versus y2 minus y1. So it kind of makes sense. Oh, I didn't use the right colors. They used red and blue. Notice the order though, and that's really important. So when they say from A to B, they're referring A as being your initial point and B as being your terminal point of your vector. And you have to subtract the x and y components in that order. So that's going to be really particular when I go to ask you for component form here today. So like this example here, your resulting vector from A to B starts with x2 minus x1, so carefully subtract negatives. 3 minus negative 4 would be a 7. And then, oh, is this one on your sheet? No, okay. And then for the y's, y2 minus y1, negative 5 minus 2 would be a negative 7. So that would be the resulting vector in component form. This is what's on your notes, right? Something like this? Cool, cool. So they give you a new formula here, and it has v, what looks in like absolute values. That's representing the magnitude of vector v, and it should look really familiar to you. Who can identify that formula for me? That is distance formula. So we shouldn't be surprised that Pythagorean theorem, distance formula, magnitude of a vector, the hypotenuse of a right triangle, like these are all the same thing. It's literally distance formula. They're going to notate the magnitude of your vector like this in your textbook quite a bit. So if you want to use that same notation, that works for me. But notice, if you already know component form of your vector, where you have an A and a B, you can shorten the distance formula to look like this. So that's kind of the nice part about doing vectors when you look at the components separately. This one is, I think it's already done for you. I mean, mostly done for you. They took all the fun out of it. So they first found component form for this vector, which goes from x to y. So they started with negative 4, subtracted 2, and got negative 6. And then they did 2 minus negative 3 and got 5. So that's their resulting vector in component form. And then to find the magnitude, we'll use that shortened version since we already found the x and y components. So it would be negative 6 squared, which would be a 36, plus 5 squared, which is a 25. And what is that, 61? I think I can add today. Is it 61? Yeah. So an approximate answer of 7.8 is fine for this problem, but later on today we're going to recognize that we want reduced radicals left in radical form when we get to something called a unit vector. Alrighty. They even graphed it for you off to the side. That was nice. So, more of the same, guys. I am going to ask you to find the component form and then also the magnitude of vector. So, let's start with component form. Just watch the order in which you guys do your subtraction. So, you have to do, because it says A to B, you have to start with the B. So, 52 minus 12 is, what, 40? And then, same order, 33 minus 41 is negative 8. That's really scary that I can't subtract. Is it negative 8? Okay, yes. All right, so there's your vector in component form. So now to find the magnitude of your vector, you use the square root of a squared plus b squared formula. So depending on, it doesn't say how to write the answer, does it? Let's go for a decimal in this problem, just because I'm too lazy to actually reduce a radical right now. So remember, you can either lose the negative, or if you keep the negative, make sure you're squaring the negative in the parentheses like so. Go ahead and give me a decimal version of that, an approximation to the tenths place. Is it 40.8? Okay. The radical itself is like 1,664, which I know reduces. I just don't really want to take the time to reduce it right now. So it's going to be more of the same, guys. We're going to have a vector from A to B. Just be careful that you're subtracting in the proper order. That's the most common mistake on these questions. Are we okay if I move on from here? We've got bigger fish to fry. Cool. I didn't get a no, so I'm moving on. All right, so we can add vectors, we can subtract vectors, and we can do what's called a scalar multiple to a vector. And without me actually teaching you any of this, you probably would have like intuitively known what to do, even without knowing what a vector is. So if you're trying to add two vectors together, you just add their components together. You add the horizontal components, get a new one. You add the vertical components, get a new one. Now, be careful on vector subtraction. A lot of kids confuse vector subtraction with what we just did. Vector subtraction is not the same thing as finding the components of vector from A to point B. So when they say A minus B, it has to be subtracted in that order. So that, I think, is a little confusing for kids, because I just got done telling you how important it was to go the other direction, but now you have to be careful of how subtraction works. So just think like a little kid would have thought. On this question right here, this is just straight up subtraction. On the previous examples, where we were finding the component form and magnitude, what you were really doing was distance formula. So keep that in mind. And then scalar multiple means they throw a number in front of your vector, and you're supposed to just amplify all parts of your vector by that number. So if I stuck a 2 in front of the vector, that means multiply each component by a 2. So of course we're pre-calc, so they're going to make you do weird stuff. Let's start off with a not weird thing. What if I just asked you to add these two vectors together? So I think this is on your notes. They just want s plus t. So here's s, and here's t. So to find our new vector, you're just going to add the horizontal components together, so that would be a 3. And then you're going to add the vertical components together, and that would be a 5. So that's a nice question. This question's already done for you, so sorry about that. But let's take a look at what they did. They started with 3 times the vector s, and then they added t to that. So right here is where they kind of distributed, if you want to think of it that way, a 3 to vector s and created 12, 6. And then when they go to add t to that result, they just do the adding the horizontal parts together and adding the vertical parts together. So again, I would argue, because you guys are so very brilliant, I probably didn't even have to teach you that. You would have figured it out on your own. But good news, we're all here. F minus g. Looks very, like, simple, right? You'd be surprised how many kids mess this one up. And I think it has to do with the fact that we just did that weird subtraction component form stuff. So f minus g, for me, because I do mess up quite often, I just write it out. So here's f, and here's g, and I'm just going to write it out exactly what it looks like. So f minus g, in that exact order, produces a resultant of, let's see, 4 minus 24 is negative 20. And then negative 2 minus 21 is negative 23. Whoops, that's a 3. You can't read it though. So that's the result when you take f minus g. Not the same thing as component form of a vector with starting and ending point. And then there's a real fun one here at the end. This is more our style pre-calc. We're going to take g. We're going to subtract twice f. And we're going to add 3 times h. So I'm just going to kind of write it out exactly how they read it off to me. So I'm going to start with g, which, where's g? The blue one, huh? So g is 24, 21. I'm going to subtract 2 times f, which if you wanted to, you can just quickly double them, but I'm going to hold off on that. And then we're going to add to that 3 times h. Oops, it's a 1, -3. So it probably would be safer if I do a lot of distribution, but you know what? Let's look dangerously. Let's try to not do the distribution. Let's see if I can handle it. 24! And then you're doing what with this next part? What does this really say? Minusing an 8. And then what does this really say? Put something in minus right there. So then we're subtracting a 3. So what is 24 minus 8 and then minus another 3? 13. Excellent. And then watch out for this next part because we got to look for the subtractions. You have 21, but careful. What does this really say? It really says a +4, so watch out for that. And then over here, this guy really says a -9. Okay, I was too cocky and confident. I don't think I can do this in my head anymore. Hold on. 21 plus 4, we said, so 25. -9 is that 16? Excellent. Look at me go. If that was my test question, I probably would have stopped what I was doing and distributed the scalars and done, you know, other math. Because I'm nervous like that. Okay. So already on the back, look at that. We have unit vectors next. So if you have a vector, and all of your vectors have a magnitude of 1, so like the hypotenuse version part of the right triangle that you're creating is always a magnitude of 1. That's called a unit vector. Now that should kind of feel familiar to you when we talk about like the unit circle. Remember the unit circle was our trig functions where we always forced the radius to be a radius of 1. And that created some beautiful trig problems. Well, this is similar in that respect where we're going to, what's the word they use here? I think it's coming up on another slide. So they're going to just compare all the vectors to each other because they're going to make their vector magnitude a 1. So you're going to be able to compare vector A to vector B. So here's what we're going to do. The formula looks really scary, but all you're going to do is you're going to take the magnitude of the vector, whatever it currently is, and you're going to divide it into both of the components, the horizontal component and the vertical component. So that's what this formula is saying. It's saying to take 1 over the magnitude and distribute it into the vector. Let's see this in action because I think it's not as bad as they make it seem. So like this is already done for you. It's from your book. They have a vector. This is him. They first found the magnitude of the vector, which they stuck with this formula, but like most humans would just use this formula and then we work with it. So if you don't mind us kind of working through this on our own, -2 squared would be a 4, 3 squared would be a 9, so that's the square root of 13. So then what they would have done was they took the vector of -2, 3, and they divided both of them by that magnitude that they just calculated, the square root of 13. But notice, that is not the final answer. What did they do to get their final answer? Because no PreCalc teacher on the planet would be happy with -2 over square root of 13. They made you rationalize it because we're PreCalc and we're weird. So then, remember guys, when you rationalize a fraction, you multiply the numerator and the denominator by the square root of 13. So that's how they're getting -2 square root of 13 over 13, and then 3 square root of 13 over 13. So the formula itself is very, this is very physics and calc based. I think they take what is really a very simple concept and make it look atrocious by using the formula, but whatever. Let's take a look at an example on our own. We'll talk about the I and J components of the vector on the coming up slide here. But let's look at this example. We have vector v, which is given to you as this, -4, -1. So the first thing we're going to need to do is figure out this vector's magnitude. So, with me y'all, let's find the magnitude of vector v by taking -4 squared, so I'm just going to write that as 16, and then plus -1 squared, I'll just write that as 1. So the square root of 17 is the length of the vector. What we're going to do now is we're going to take our vector and we're going to divide each component by the magnitude. Now square root of 17 doesn't reduce at all, so you don't have any reduction, but you do have to rationalize this for me. I'm going to want you to, and I think you guys are very good at this, so I don't know if you necessarily have to like write this part out. I will in case you need it for your notes. -4 times the square root of 17 all over, this will reduce to a 17. So the unit vector is that. And then over here, it's, oh, it looks like I crossed that off as the vector bracket. Negative square root of 17 over 17. Gross. Doesn't look much better, does it? But now what you would be allowed to do is compare two different vectors together because they have the same magnitude. I don't know if that excites you or not, but it's something you have to do. Do you guys do this in physics? Did you do unit vectors at all? Okay. But not unit vectors? Didn't have any application for it? Okay. That's all right. Maybe next time. All right, so let's find, this one's real boring, because what's the magnitude going to come out to? If you have a 3, 4, it's going to be a 5 on the magnitude, the hypotenuse. So that's like, I mean, it's really pretty. Let's look at this one, though, just because there's more fun to do. So let's find the magnitude of vector W. So let's see. This time I don't want a decimal. I want you to leave it as a radical, and I'm going to need you to reduce it as well. Bad news for everybody. So that's 625. Is that 725? So I know 725 is divisible by 25. What's 725 divided by 25? Is it 29? Okay. So this is 5 times the square root of 29. That's the magnitude that we're going to be using when we go to divide. So we're going to take our original vector of 10, 25, and we're going to divide each component by this dude. So now we have the added layer of fun, because not only do you have to rationalize this, but you're going to have some reduction as well. Let's actually do the reduction first. If you look at your coefficients on this first component, you have 10 over 5, which obviously that's just going to reduce to a 2. And then similarly over here, 25 over 5, that'll reduce to just a 5. So right now, your vector says 2 over the square root of 29, comma 5 over the square root of 29. But there's not a pre-calc teacher on the planet who'd be happy with that. So you're going to hit top and bottom, numerator and denominator, by the square root of 29. And you get 2 square roots of 29 over 29. And 5 square roots of 29 over 29. Guys, I apologize for skipping the actual rationalization step. I will go through and show it if you want me to. Any takers on that? Because we're just very good at that in trig. So, yay. Alright. Here we go. Something weird. This is from your book. So unit vectors in the direction of the positive x-axis and positive y-axis are denoted by I, which equals 1, 0, and j, which equals 0, 1. Now, right away, your brain probably goes to I like imaginary, and the answer is no. This is not imaginary, complex number I. The way that you can tell it's different, in your textbook, they use like a really blocky looking I that's bolded. And in your textbook, when they refer to the imaginary number I, they make it almost cursive and it's very much italicized and it's not bolded. So if you look in your textbook print ever, I components for this stuff are like big, bold, weird, blocky I's. They're still lowercase. I kind of wish that math would just figure out what they want to call things and maybe not call them the same letter. That would be fantastic, but you know, whatever. There's actually some countries around the world that call imaginary numbers J. And actually in electricity, I believe they refer to them as J sometimes. So that's fun. Has nothing to do with I, but it's good to know. All right, so here's what we're going to be able to do, guys. Instead of writing your vector in component form, we can just sneak an I and a J attached to the horizontal and vertical components, and that's called a linear combination technically, but that's another way to denote those same vectors in component form. So it would make your math a lot easier to do math with this form. That's why they have that form. That's why we all accept it. You can do some serious systems of equations if you have that form. All right, so the idea here is we're back to that idea in your book about going from point D to E on your vector. So this is a very specific direction, which means you have to start that weird subtraction formula with the secondary horizontal component. So they said take 4, subtract -2, and that's how they're getting a 6. And then similarly, they're saying start with 5, take away 3, and that's how they're getting a 2. So that's the vector in component form, but then they said, oh, we can do it this even better. Instead of writing it in component form, you can take the horizontal component, stick a blocky I after it, plus the vertical component with a j after it. So in your book, when you see 6i plus 2j, you have to know that that's equivalent to the vector 6 comma 2. So let's see you guys do this. Oh, that one's already done. I hate when they do that. You see how they got the numbers? Because I'd like to try one on our own now. There we go. So notice this is M2N, so be careful. It is definitely in that direction. So you have to start with the second one, okay? So the horizontal component is -5 minus 2, which would be a -7. And then the vertical component, you got to start here. So -3 minus 8 is -11. So that is the vector in component form. Now they say go ahead and write it as a linear combination with I and j. So you go, all right. So -7 with a blocky I after it. And then instead of saying plus -11j, most of us would just say minus 11j. Ta-da! All things that I might ask you to do on your homework. All right, where are we at? Okay, time to break out the unit circle. Now, what if I give you a clue about the magnitude of a vector and I give you the direction of its angle? So that's going to become important to us if we go back and we remember this formula from yesterday. So remember, guys, yesterday, component form for a vector, the horizontal component was the magnitude times the cosine. Remember the bearings yesterday? And then the vertical was the magnitude times the sine. So we're going to use that same formula today, but this time, instead of having a horrendous application to go with it, it's just like go look at your unit circle and figure it out. Okay, so these should be easier than yesterday. I'll put it that way. This one's already done for you. So 10 times the cosine of 120. Well, you just peek at the unit circle if you weren't sure, but at some point in your life, you should be able to figure out that the cosine at 120 is -1/2. And then 10 times the sine of 120. Again, you could either peek at the unit circle or you could figure it out yourself, but it's square root of 3/2. And then, of course, math teachers are going to want you to simplify. So 10 times -1/2 got you -5. And then 10 square roots of 3/2, they cross-canceled or reduced the 10/2 and created a 5 times the square root of 3. So I think that kind of is almost our last task. We only have 2 more tasks on this lesson. Don't you kind of feel like I should have started with this lesson? Maybe we all would have been less depressed about the bearings. I'm sorry. My bad. Okay, so 11. Please give me an exact answer for 11, but we're going to find out on 12. There's no such thing as an exact answer for us because we have a weird angle. So this guy, when I go to find the horizontal component, you start by taking the magnitude of your vector, which is 18, and you're going to multiply it by the cosine of your angle. And then for the, that was for the horizontal component. For the vertical component, you're going to take the magnitude of your vector, and you're going to multiply it by the, the sine of your angle. All right. Well, I guess it depends on how much you love your trig unit circle. I will tell you that your calc teacher has requested that we all brush up on our unit circle memorization before calc hits us. And that's going to be one of the major tasks that you guys have as you are getting ready for calc over the summer. I know some of you are not taking calc, but it's one of the things we're going to be asking you. Actually, Hoffbauer and I are going to be checking in on you guys to make sure that you are brushing up on your unit circle. We haven't told you that yet. That's a little sneak peek. All right, 18 times the cosine of 240. What is the cosine of 240? Say it again. -1/2? Okay. And then this must be negative square root of 3/2 then? Am I in the right quadrant? Yeah. Okay. Do I have the wrong trig function? Are we good? Okay. So, of course, they want an exact answer, so we simplify. So 18 times -1/2 is how we're going to get a -9. And then over here, 18, but remember you're dividing that coefficient by 2. So that's -9 square roots of 3. And then it just says write it in component form. If for some reason they got weird and they were like, I also want you to write it in that linear combination form, that wouldn't be that hard. We just stick an I and a J on the end of them. So they didn't ask that though, so we're just going to stop here. Now this one, you're going to have a tough time finding 95 degrees on your unit circle. Like, super tough. Like you won't. So since we can't find this on our unit circle, unless we wanted to use sum and difference formulas, which I do not, we're just going to get an approximated answer, which means decimal on your calculator. So make sure you're in degree mode before you do any typing. But the same formula is going to be applied here. So we have the magnitude times the cosine of 95 for the horizontal component, and then the magnitude times the sine of 95 for the vertical component. You'll have to type them in separately, obviously. Is it like negative 0.44 for the first one? And then about 4.98 for the vertical one? Cool. Again, things that you'll see on your homework and subsequently on your next summative. And then here's where we're going to tie it all together. What if I give you the weird IJ thing? What does that mean? Are you going to be able to find the vector's direction? And can you, well, I guess that's all they want, just the direction. We could have found the magnitude, I'm just not going to bother. So they're reminding you guys that if you have a horizontal and vertical component, which we will, you could use a tangent function to find an angle. That would be the one we'd set up. We could do cotangent, but no one does that. So tangent. So keeping that in mind, they've done a couple from your book. Let's go look at our examples though. I'm going to start by actually kind of plotting this out if you don't mind, because I love a drawing. Even my drawings, they're terrible. So negative 4I plus 2j is equivalent to the vector negative 4, comma 2. So if you think about where that vector would be located, that would be, left 4 units and up 2 units. So obviously we are in the second quadrant. Keep that in mind when we're thinking about our right triangle that we're about to come up with. And I know it's not proper to call a leg of a triangle negative 4, but I'm going to do it anyways. So when I ask you to find an angle, the only thing you're going to be able to set up for me with the right triangle trig right now is going to find this weird little green angle here. So we're going to set up, I'll go ahead and just say the inverse tangent because we know what we're going to do. Just like with our bearings yesterday, the inverse tangent of, make sure it's the vertical, whoops, that was positive 2, Abruzzo. Good Lord, I'm going to get the wrong sign. All right, positive 2 over negative 4. And on your calculator, what does your calculator spit out to you? Is it negative 26.6? Okay. So think about what your calculator is giving you and why is it giving you that angle. It just gave you negative 26.6, which is this angle right here. Why? Yeah, arctan is only defined from negative 90 degrees to 90 degrees. So your calculator will only give you something here or here. And because we had a negative tangent, it was giving me this one down here. So that doesn't mean we're like out of luck. We can still figure this out. Remember, vertical angles are congruent. So if this is 26.6 degrees as far as a distance, that means so is this one. So what I need from you guys is a directional angle from the horizontal, from standard position. How are you going to figure that out? This guy all the way over here is 180, right? If I went all the way to the axis. So we just need to back it up 26.6 degrees. Did I have the right angle? 26.6, yeah. So 180 minus 26.6 will give you 153.4. That's the directional angle for that vector from standard position. Don't get weird and creative and start doing like, north of west stuff. Just call it 154.3 and be done. All right, number 14. Let's draw it. Clearly it's in the first quadrant. 217, sure. To scale as always, Abruzzo. My goodness, it's like they're getting worse. All right, this is 2, this is 17. We know we're going to be setting up inverse tangent again, and inverse tangent will be giving us that angle right there. I think this is great news, guys, because the angle that your calculator is going to spit out to you is going to be the right angle because inverse tangent is defined in that quadrant. So make sure you're doing vertical leg over horizontal leg. And we should get, is it 83.3? Which is that is from standard position, so we're done. Okay. And that's the end, children. We have 11 minutes left, so now tell me what homework questions you have. You want to look at that one, Hunter? It was 7. Want to look at that one? Okay. On worksheet 2, which I think I have somewhere. Where did I put that? Vectors day 2, I think it's there. All right, so worksheet 2, remember the whole worksheet is assigned to you now, so whatever we didn't get done is for you to do on your own. There's a request for number 7, which is on the back. A good orienteering question. I love these. So, I like to draw very separate coordinate planes for mine. My vectors are very ugly, and if I put them on top of each other in the same coordinate plane, it gets really gross. So, if you're trying to save room, though, because there's not a ton of room on all these worksheets, you can put the first 2 vectors together on the same coordinate plane. I'm not going to, though. So the first one, Jada walks north 70 degrees west for 200 meters. So this sort of notation means that you start on the north line and you move towards the west 70 degrees. So if you started here and moved 70 degrees towards the west, you're going to end up right there. So if you wanted to call this 70 degree mark right here, that's fine, but I think what's going to be more important to us is how big this angle is. How big is this angle? It's going to be 20 degrees, right? We'll come up with an actual theta in a minute. Actually, let's do that right now. Standard position, how big is that? That's a 160 degree angle. So when I go to write my vectors in component form, I'm going to need to use 160. That's the only catch to using component form, is you have to be from standard position. So for her next part of her trip, she's walking due east for 90 meters. So this would be east, 90 meters. What's your theta? What angle are you at if you're just sitting there? 0, yeah. And I have done a terrible job, as always. I forgot to mark the actual magnitude. So this was 200 meters, and this was 90 meters. So the vector components for this first part of her trip would be 200 times the cosine of 160 and 200 times the sine of 160. The vector components for this part of her trip would be 90 times the cosine of 0 and 90 times the sine of 0. And to figure out her total resultant trip, we're just going to add them together. So, decimals are fine here, although I think it's not really all decimals. I need you to add these components together. And I know some of you are looking at this 90 degree or 0 degree one going, well, this is really easy because the cosine at 0 is 1 and the sine is 0, so this is just going to be like 90 comma 0. Go ahead, do that in your head if you want. I'm just going to type it on the calculator because I'm lazy. So who got a horizontal component for me? Yeah. So negative 97.9 meters. And then a vertical component was 68.4. So they want to know how far and at what bearing is Jada. So they want me to continue on with my resulting vector. And this is the most crucial part for kids. If you have not drawn anything on this picture yet, this is the part you absolutely should definitely draw because you're going to get it wrong if you don't. Where is negative 97.9 comma 68.4 located? Second quadrant, yeah. And I should be graphing it relatively to size, like the negative 97 should be longer than the 68.4, but, you know, I'm not going to be able to do that. So just pretend. It's all about labeling, right? I know it's improper to call the triangle negative. I don't care. So when they want to know how far she traveled, that's just defining the magnitude of the resultant vector. So you could use that new shorter formula today, or you could just think of it as Pythagorean theorem. They're all the same thing. So, is 119.4? Thank you. And at an angle of, okay, here's the problem. When you use right triangle trig, and you try to find this angle, that's a great angle to have, but it's not going to be a bearing. So go ahead and use your inverse tangent. Tell me what your calculator spits out, because it's not going to be the thing I need. Oops. Negative 34.9. So again, your calculator is programmed to only give you angle measures for inverse tangent between negative 90 and 90. So it's giving you this angle. So here's what you guys need to remember. When you give me a bearing direction, you have to choose what method you're going to answer it with. You could go, like I think in my key I put north of west. You could do a literal true bearing. You can say from standard position, which is my favorite personally. I like from standard position because it keeps my brain focused on that. I think you guys could very quickly figure out this blue angle. Isn't that just 180 minus 34.9? And what is that number? Because I didn't calculate that one. One more time, I'm sorry. Thank you. And you could maybe notate it that it's from the horizontal or from standard position. The key has like a weird, like, is it like 34.9 degrees north of west or something? That's fine. If you wanted to go crazy and give me a true bearing, I know my kids who came from trig, they were always asking you guys to give true bearings. So you would have had to have done a true bearing of, let's see, this would be like 270 plus another 34.9, whatever that is. So that would be an acceptable answer, is my point. There's not just one way to write the answer. All right, I have time to do another. Anyone run into trouble and want to look at it? Well, you guys can just get started on your other homework if you want. So tonight, your homework. I don't think this is right. What does your homework really say? Ugh. Miss Hoffbauer, she rocks. She already copied the bookwork for you. Oh, it's not even close to right? We did 1, 5, 11, 13, 21, 28. She picked better problems for you, too. She's a doll. All right, 38, 39, 45, 51, and 53. Okay, cool. That is your homework tonight. I know it looks really long, but think about some of the work we did today. Problems took like 3 seconds. They were done. Okay? All right, good luck.